can definitely start now. So it's a great pleasure to have Professor Chelsea Sharon from UYale-NUS to tell us about her work, about supermassive black holes and stars. So Chelsea is an observational radio astronomer. She's worked on a lot of different things. Worked, for example, in the Very Large Array in New Mexico, and the Sub-Millimeter Array in Chile. And so work is very kind of foundational. It addresses very foundational questions about the formation of the early universe and galaxies. And I think it's a great chance for us here. We don't really have an astronomer, and she's probably one of the only astronomers in Singapore, if not probably the only, maybe. I think it would be really great to hear from her about what she's been doing. So let's welcome Chelsea. Thanks very much.
Great. Thank you all for having me and giving me the opportunity to talk to you all a little bit about my research on galaxy evolution. So I'll be talking to you about kind of one of the main two threads of my research, which is basically the roles of galaxies' central supermassive black holes in ending periods of extreme star formation. So I'll start very broadly, just kind of motivating the work that I'm doing, and talk a bit about the methods that we use before showing some of the results that I've gotten recently, including some work with the first two collaborators listed, Cabran and Rennie, who are undergrads here at UYale-NUS. Cabran recently graduated and started his PhD over at Yale, and Rennie is finishing this year. All right, so the basic sort of fundamental motivation for my work is basically the big question of why do the galaxies that exist today look the way that they do? And so if you take an image with the Hubble Space Telescope and point it at the most empty patch of sky we could possibly find and stare for hours and hours and hours, this is the image that you get. And every single dot in this image is actually an entire galaxy with billions of stars on their own at, some of them relatively nearby and some of them far away. And there are some basic kind of qualitative features that you can see. So we, have basically spiral galaxies. So these look like disks. So dinner plates, they often have beautiful spiral arms. They're usually like bluer on the outside edges because of younger star formation, and they're redder in the center where all the young hot blue stars have died and leave these older redder stellar populations behind that are much lower mass and therefore cooler. You have things like elliptical galaxies that are much more massive. They have no spiral arms or notable features. They're kind of shaped like an American football, except with the corners rounded off on the edge. And they really don't look like much. They're pretty boring looking, but they're also very massive compared to the disk spiral galaxies. And then you'll see things that look like this, sort of cosmic train wrecks that you can't really give a necessarily fixed shape to, and they're just kind of a hot mess. And so what we really want to understand is, why do we see this diversity of galaxy types? Why do they have the properties in terms of their colors, their stellar populations, their masses, and their dynamical behaviors? And we have some rough idea of how this works because of what we know about cosmology. So lambda CDM cosmology, which is very cleanly predicts the numbers of galaxies that we expect as a function of their mass. And so this is a plot of the number of galaxies per unit mass per cosmological volume, a co-moving megaparsec. And the predictions from, based on how much dark matter there are, is basically a straight parallel line. But when we actually observe galaxies' stellar mass, it doesn't follow that same shape. It shows the sort of broken power law curve. And so that's a major problem for the field of galaxy evolution. And so, we know that even though we don't really necessarily know what dark matter and dark energy is that gives us the sort of energy content of the universe, we know roughly how it behaves. So we know the composition of the universe in terms of energy quite precisely. And so this is through a combination of observations of the cosmic microwave background, the small scale fluctuations in the afterglow of the Big Bang, that's at about 2.7 Kelvin. We can also constrain this by using specific types of supernova that explode at a very well-known brightness. So that means that they're observed, we can compare their known brightness to their observed brightness and tell us precisely how far away those are. And then baryon acoustic oscillations, which is basically the distribution of matter on the largest scales of the universe. So all of these little dots here are individual galaxies that people have mapped out in sort of a pie slice looking through the universe. And that tells us quite precisely that most of the universe is dark energy. We don't know precisely what it is, but we know it acts roughly as some sort of repulsive force proportional to the amount of empty space there is. We know about a quarter of it is dark matter. Again, don't know what dark matter is. It's an active area of research, but just like regular matter, it attracts things gravitationally. And it doesn't interact with light, which is why we refer to it as dark. It's because we cannot actually see it visibly. We can only measure its gravitational effects. And a relatively small fraction is what we usually refer to as just baryonic matter. So that's the stuff that you and I and the trees and the stars and the planets are all made out of. And that behaves in the way that, pretty much the rest of physics studies. And the tiny, tiny fraction is the very fast things like photons and neutrinos. And that's present day. But based on how we know dark energy behaves and how dark matter attracts other particles with mass gravitationally, we can do simulations. So this is a dark matter simulation. So it starts at very early universe. So this redshift, it decreases to the present day, and you can see the time since the Big Bang in the top corner. And so basically the universe started, if you watch the Big Bang theory, in a hot, dense state and expanded, and it was pretty uniform and boring, except there were small patches due to early sort of quantum mechanical fluctuations that had early overdensities and underdensities. And so these overdensities would gravitationally collapse and the underdensities would gradually rarefy. And what happens is that all of the dark matter and regular matter kind of ends up cooling into this vast filamentary structure. It kind of looks like a big spider web. And so we often will refer to this as the cosmic web. And so this huge spider-like structure that shows sort of the density of dark matter is also where all the galaxies form, usually at the nodes where these dark matter filaments connect to one another. And so in principle, each one of these sort of round, blobs, we refer to them as dark matter halos, could host a galaxy inside of them of different masses. And the larger mass dark matter halo you have, the larger mass galaxy that should go inside of it. So skipping ahead, we're almost to the present day. Redshift 1 is something, it's very nonlinear. So that's something like, 5 billion years since the Big Bang. So about 8 billion years until today. So this is still fairly early in the universe, but it kind of just looks like this as time goes on to make a larger and larger dark matter halo. Oops. Okay, so again, each of these halos and all of their sub-halos contains a galaxy in principle. And for something like the Milky Way, our own galaxy, which is a pretty average galaxy, it won't be found in one of these giant nodes. It'll be found at some one of these smaller innocuous nodes. And so for something that's about 1 megaparsec inside, so a parsec is about 3 light years for reference, the Milky Way would be approximately this size and scale because, baryons interact with light and can cool. So they tend to only be found in the very cores of these dark matter halos. So in principle, if we simply paint on the regular matter in proportion to these halo masses, the mass inside of one of these big elliptical dark matter structures, you should be able to predict the number of galaxies as a function of mass, but it sort of overpredicts the number of galaxies from what we observe. So returning to this plot, we want to understand why this distribution of galaxy stellar mass does not match that we get from these dark matter simulations. So there are a bunch of potential solutions. The first one is that we actually don't understand dark matter, how dark matter behaves. This is a thing that we have to always keep in mind, that maybe we're missing some fundamental physics here. But we can't really make progress with that assumption. We have to wait for our rest of our physics colleagues to work on that problem a bit more. So we're just going to conveniently ignore that one. And then look at some of the other solutions. And so the first one is obviously that, as you saw from that big pie chart of the cosmic energy density, there's just not as much normal matter as there is dark matter. And so that gives you an offset of this power law relation. And then not all of the normal matter will end up in stars, because in this red curve, we're actually probing specifically galaxy stellar mass. As we saw in those pictures of the elliptical galaxy at the beginning, we saw these sort of filamentary structures that give these spiral arms. That's dust and gas that's inside of these galaxies that has not yet turned into a star. So, okay, that gets us sort of the normalization, but it doesn't get us to the right shape yet. We think at the lower mass end here, it's what is known as feedback from star formation. So let's talk a little bit about how star formation occurs in galaxies so we can understand this depression on the lower mass end. So this is sort of a picture of the star formation cycle. And starting on the left, we have what is we refer to as the intergalactic medium. So the gas that's in between galaxies, and it follows this filamentary structure that we saw based on the dark matter simulations before. All of that gas is ionized, and again, most of the universe is made out of hydrogen helium, so it's mostly ionized hydrogen. So a bunch of protons and electrons in this sort of filaments. It gravitationally, it interacts gravitationally, and it will cool and to form atomic gas as it flows along these filaments into a node where it eventually forms a galaxy. And angular momentum is conserved, so oftentimes it will result in a disk galaxy if there's just any sort of slight, preferred angular momentum for the direction of the filaments going in. Within the now atomic gas that's inside of these galaxies, there will often be little tiny overdensities in that. It's not perfectly smooth, and so that will gravitationally collapse, and it will also cool and form molecular gas, so a lot of molecular hydrogen. And these molecular hydrogen clouds, again, it's very fractal in nature, so there's even smaller overdensities there, and those gravitationally collapse to form stars or clusters of stars within these molecular clouds. So stars, when they form in a molecular cloud, will form in a wide range of masses. So things that are maybe 10% of the mass of the sun to things that are potentially 100 of times more massive than the sun. And these most massive stars, they live fast and die hard. So they don't survive for a particularly long time. They burn through their fuel and then they go supernova. And when you have a cluster of stars where a certain fraction of them are particularly high mass and a lot of them are going supernova at the same time, they'll actually end up disrupting their stellar birth cloud. And if they have enough of this going on at once, you can actually create vast winds coming out of a galaxy. And so in this sort of multi-wavelength picture, the green is sort of the optical starlight from an edge-on disk galaxy, which is why it just kind of looks like a line. The blue is actually the hot X-ray gas from all of these stars exploding at the same time. And the red here is infrared from the dust and gas that's sort of left over, so the shredded birth clouds that's being pushed out by these vast winds of all of these stars going supernova at essentially the same time. These winds will therefore eject some of this molecular and ionized gas, plus all of the heavy elements that have been fused inside of these stars, thus polluting the intergalactic medium with the heavy elements that are so critical to planets and life and that sort of thing. And eventually it can fall back down onto a new galaxy, and it does this whole entire cycle over again. And this is sort of what has led to the proliferation of what astronomers refer to as metals, i.e. anything that's not hydrogen or helium is a metal, into the rest of the universe. Now, if your galaxy that has these winds is very low mass. It doesn't have a particularly deep dark matter potential well for all of these gases to escape. So for a low mass galaxy, you have enough supernova going off, and basically this part of the star formation cycle is broken. So all of the gas would end up leaving that galaxy and not falling back down onto it to fuel future generations of star formation, and it just ends after one sort of burst of initial star formation. And so that helps explain this low mass end here. So for this higher mass end, we need something else. And this is where this idea of feedback from AGN occurs. So what exactly is an AGN? So an AGN stands for an active galactic nucleus. So nearly all galaxies, except for perhaps the very, very smallest, have a supermassive black hole at their center. And we know that very well. So this little movie on the left is from the group at UCLA that just won the recent Physics Nobel Prize for proving the existence of a supermassive black hole in our own galaxy. And so these little dots are tracing the positions of stars in the center of our own galaxy as they evolved over as their position changed over several years. And they're all orbiting a common center, which has no emission. And so there has to be, you can just constrain with Kepler's laws, a massive object here that they're all orbiting, but it's not glowing at any wavelength that we can see. And so we infer that it must be a black hole. So black holes that are actively eating some of the gas in their galaxy are called active galactic nuclei. So that's all it is. An AGN is a supermassive black hole that is currently consuming material from its surrounds. Active galactic nuclei were sort of discovered in the 1970s, I want to say, because basically they're extremely bright and they're extremely compact. Many active galactic nuclei, if they're bright in the optical, will outshine their host galaxy by factors of 10. In fact, some of the earliest AGN, when they were finally doing like large scale optical surveys, they're not super duper common, but when they were doing these surveys, they actually thought they were some sort of peculiar form of star because they were so bright and so compact, and they didn't have the contrast in their images to see the galaxies that they were in. So they referred to them as like quasi-stellar objects, or if they had radio associated with them, quasi-stellar radio objects or quasars. They were also interesting because if you looked at their spectral lines, it inferred very large velocities relative to our own galaxy, which meant that they're pretty far away. So these very unique high energy sources we think must be associated with supermassive black holes, just because only supermassive black holes have a deep enough of a potential well such that stuff falling in could release that much energy. So in terms of the structure of active galactic nuclei, we think they're basically shaped kind of like a donut. So there's a dusty torus. Again, thank you, conservation of angular momentum. Things tend to form sort of disky when they fall in and cool and torque each other, all the various clumps of material. So what you see when you're looking at an active galactic nucleus depends a lot on viewing angle. So the ones that are very, very optically bright is when this sort of donut-shaped material is looking at you fairly face on, so you can see the brightest parts of the accretion disk right near the center as that material heats up and collides with other particles right before it goes in. So it turns out that supermassive black holes, rather, contradiction from the popular conception of them being something that eats all light and therefore you can't see them, are actually some of the brightest things out there, just because their accretion disk is so darn bright. But if you look at the system slightly more edge on, you might not see down to the bright accretion disk right near the event horizon of your black hole, and instead you'll see this hot glowing material of dust, disk of dust. So many active galactic nuclei are found in these giant elliptical galaxies, and oftentimes those have these vast radio jets associated with them. We don't really understand too much about radio jet formation, but since we have ionized material traveling in circular paths. That's, roughly current loops. So there must be magnetic fields, and we've got big, gigantic, twisted magnetic fields. And so that's accelerating some charged particles. And this is all synchrotron emission that we're observing in the radio, is sort of the rough picture there. And they're huge, like they extend many times further away than the actual size of the stars in the galaxy. So they're quite violent, energetic events. Not all AGN in elliptical galaxies have radio jets, only some of them do. And some disks also do have AGN in them, but they typically do not have radio jets. So there's kind of a whole complicated ecosystem of classifying different types of AGN. But fundamentally, they're all the same thing. They're different viewing angles of this dusty torus with or without a radio jet. So that's an active galactic nucleus. Again, extremely bright because of just how much energy is released when you're, having a lot of material fall into a very, very deep gravitational potential well and heating up and speeding up as all these particles collide with one another before they eventually fall into the black hole. So since we have this, very high energy region that's preferentially found in some of the more massive galaxies, we think this might have something to do with this suppression of the number of stars being formed in the more massive galaxies. So this is sort of our rough cartoon picture of how we think this works. So in the early universe, you have some proto-disk galaxies that have some normal amount of gas and some normal amount of star formation in them. They're in their individual dark matter halos, and eventually they're falling along those cosmic filaments until they collide at a node, and you get a galaxy merger. When you have this big galaxy merger, there's huge torques on all the material, and it eventually sort of funnels all of the gas down into the very center of this gravitational potential well. And the giant clouds of gas smack into one another because they actually have some appreciable cross-section, unlike a star. Stars don't typically run into one another, but the gas clouds do. And that causes this big burst of star formation because you're taking these big clouds and ramming them into one another. And so once you have a lot of star formation going on in this central part of this galaxy merger, a lot of that gas is consumed by the rapid star formation, but some of it goes into the black hole and fuels this AGN phase where AGN feedback happens. And I'm kind of waving my hands for a reason because we don't really understand it. And I'll get into that in a moment. But basically, since these galaxies are smashing into one another, they don't necessarily have nicely aligned angular momenta, and so all the orbits of the stars get mixed up, and what you're left with is a giant elliptical galaxy, which, because of the star formation and the AGN feedback particularly, there's no more gas, there's no more star formation, there's no more AGN, it's just red and dead and sits there for forever. It's roughly the idea. And so as time goes on, you should have more and more of these red, dead elliptical galaxies. And so there are multiple lines of feedback that are suggestive and circumstantial that that AGN might play a role, other than the fact that they're just the most energetic things out there that could potentially suppress star formation in these giant galaxies. The circumstantial evidence includes that they're most common in the higher mass galaxies, and particularly these galaxies undergoing mergers, which drive these high star formation rates. In the local universe, these elliptical galaxies masses, and then the central sort of bulge region in a disk galaxy, the part that's dominated by these red stars, actually their mass tightly correlates with the mass of the central supermassive black hole. We usually are probing this mass via dynamics, so we're looking at the velocity dispersion of those red stars, and so we refer to this as the M sigma relation. And so in the present day, we see this really tight correlation between the mass of the bulge and the mass of the black hole, which suggests that the black hole is growing at sort of the same rate in some sort of tightly correlated way across cosmic time. The few measurements that people have been able to make of black hole masses in the early universe and bulge masses in the early universe show that there is some offset from this relation for galaxies that are undergoing starbursts earlier in time. And so there has to be some correcting factor that produces the present day relationship. Also, if you look at the sort of star formation rate history of the universe and the black hole accretion rate history of the universe, they seem to sort of track one another. So this is a pair of plots from Hopkins and Beacom. It's a classic review paper. This is known as the Lilly-Maddow plot. And so if you look at the star formation rate density of the universe on average over large cosmic scales, so again, this is per co-moving megaparsec, so we're factoring out the expansion of the universe. The star formation rate today, which is shown on the left, has actually declined by more than an order of magnitude from about redshift 2 to 3, so which is about 10 billion years ago. And there is some ramp up presumably before that, though there are larger uncertainties and porous statistics when you go earlier and earlier in cosmic time. If you do the same thing to map the black hole accretion rate as a function of cosmic volume, you see a similar peak at sort of redshift 2-ish, 10 billion years ago. And that's inferred by just how bright the AGN are. So if we really want to understand why we have this underabundance of massive galaxies relative to what we expect in dark matter, that means we really need to understand this process of AGN feedback, where it most likely had the biggest effect on what was going on. So that means studying these galaxies that are about 10 billion light years away, and therefore 10 billion years ago. So how does this AGN feedback process that I sort of waved my hands at work? Well, there are basically two classes of feedback. The literature isn't very consistent in its naming convention, so it's called, depending on what you're reading, the kinetic mode, the jet mode, the radio, the maintenance mode. I tend to classify these as all an indirect mode of AGN feedback, and then there's a radiative or wind mode, which is a more direct mode of AGN feedback. So this indirect mode has to do with these radio jets. So basically these vast radio jets are adding energy into the hot, tenuous gas in the dark matter halos of these galaxies before it has cooled onto the galaxy itself. And so we know this happens. We can see it. So this image over here is an X-ray image produced by all of this hot, extremely hot, tenuous, ionized gas in these halos. And you can see these like shock fronts and sort of regions kind of carved out of this gas. And that's from previous epochs of radio jets coming from the central galaxy, adding basically a bunch of kinetic energy to this gas to prevent it from cooling down and fueling star formation in the galaxy in the center. The problem with this is that this seems to only really be important for the most massive galaxies. So we see this effect in galaxy clusters. So the largest gravitationally bound things in the universe, it's not a single galaxy, it's an entire cluster of galaxies that's being affected by these giant radio jets. While we see radio jets on smaller scales, they don't necessarily show this giant effect in all of this hot halo gas for smaller systems. Partly that's probably a sensitivity issue because we just can't detect necessarily that low luminosity of the X-ray emitting gas in these smaller systems. So it's probably partially a selection effect. But it seems to really only matter for the largest galaxies out there. And again, not every AGN has a radio jet. So it can't be the only thing that's going on if not everything has it, has that radio jet. So the second mode is this more direct radiative wind mode, where basically the photons produced by this hot accretion disk right next to the supermassive black hole actually just physically pushes dust and gas out of the galaxy, much like the supernova do for star formation feedback. So it's all sort of a negative form of feedback. And so the great news about this more radiative wind mode is that, again, outflows are extremely common. We see absorption spectra from these shock fronts of this tenuous gas as it's being pushed out of the galaxy. that's all blue shifted as that wind is coming towards you and illuminated by the background source that is the galaxy. And so we see them all the time. The problem is that it's very hard to distinguish between an AGN-driven and a starburst-driven wind. Since AGN and these bursts of star formation tend to occur near the same time in the evolutionary path of these galaxies, we can't really disentangle that effect necessarily so well. There's also just the conceptual problem of how do you couple all the radiation from this very tiny region in, the central, maybe tens of parsecs right near the black hole, to gas that's potentially tens of kiloparsecs away from it. So just the physical scales there don't necessarily make sense. The other issue is that most of these AGN winds that we see are usually observed in ionized and atomic phases of gas, not the molecular gas that is the stuff that's actually involved in star formation. So there are some conceptual issues with this particular type of feedback as well. And that's also ignoring potential mechanisms like these winds or the jets just adding turbulence to the interstellar medium within these galaxies, or disrupting the molecules by the harsh radiation fields as well, that could potentially also affect this process of star formation, where these molecular clouds are cooling and collapsing under their own weight to form a star. So if AGN feedback should be happening in these most massive galaxies early in cosmic time, and we think it's happening via direct mode, we should be able to see some sort of signature observationally in the molecular gas, this fuel for star formation. So that's sort of how we get to what I do, which is using these molecular lines to try and understand how AGN might be influencing star formation in these galaxies. So let's talk about how I characterize the molecular gas in these galaxies. So it's a form of remote sensing. Obviously, I can't send a spaceship to another galaxy and go take a sample of gas. So I'm just measuring spectra with my telescope here on Earth. So again, most of the gas out there is, molecular hydrogen. And molecular hydrogen doesn't actually strongly emit at the typical temperatures and densities of these star-forming molecular clouds. They're usually something like 10, maybe 50 Kelvin in temperature, and molecular hydrogen just doesn't emit very strongly. So we have to use a tracer species. And so the next most abundant tracer is carbon monoxide. And what's great about carbon monoxide is that it's a pretty stable molecule. It's a triple bond. It's got a really nice, strong dipole moment. And the rotational transitions are really easily excited by collisions with the molecular hydrogen. And so the transition to the J=1 to J=0 rotational states is something like 115 gigahertz. So that means we can observe these things with radio telescopes. What's also great is that this line luminosity is actually linearly proportional to the gas mass. And so a bunch of work has been done to sort of calibrate how bright one of these spectral emission lines are to a specific mass of gas, including the molecular hydrogen. And as the gas is, if you're observing warmer or more dense gas, then obviously the distribution of emission lines will change relative to one another. So you get more of your CO in these higher excited rotational states in these warmer and denser phases of molecular gas. So that means what you can do is, if you observe multiple rotational transitions, you can sort of map those onto a model of the temperature and density of the material, and determine actually what are the physical conditions of the gas in these very distant galaxies. So only in sort of the last decade have facilities had the right instrumentation capabilities to really do this for galaxies in the early universe, right? So the ground state is 115 gigahertz, but these are at redshift 2 to 3. So that means that I'm observing at something like 30 to 35 gigahertz, typically speaking, if I'm observing the ground state. And so when they upgraded the Carl G. Jansky Very Large Array, astronomers are again creative at naming things. It's dark matter, it's a very large array. So let's just call it the Very Large Array. So this is in New Mexico. When they upgraded it, they finally got these Ka band receivers, so we could do CO1 to 0 studies in the early universe. People had been doing since the early 2000s some of these higher J transition lines at smaller arrays with only sort of like 6 or so antennas. And that allowed them to get some of these CO transitions for the very brightest systems, but it was only in sort of the last, let's see, we're on cycle 8. So I guess in the last 8 years that ALMA, the Atacama large millimeter / submillimeter array in Chile could really do the high sensitivity stuff where we could probe these molecular emission lines in more normal galaxies and not just the biggest, brightest things out there. So that's led to kind of an explosion of studies and of CO lines in these high redshift galaxies. And so that's the main tool I end up using for my research is these spectra we get through radio telescopes. So there are different ways that we can potentially look for these feedback signatures. So I basically kind of class them as something you could do with just an individual CO line or something where you need multiple carbon monoxide lines. So one thing that you might expect if AGN feedback or suppressing star formation is that AGN would just have less gas in them, period. It turns out that that's really hard to establish because of mass biases. So what that means is one of the most fundamental correlations of all extragalactic astronomy is brighter things are brighter. So that means regardless of what wavelength you're looking at, if you're doing some other tracer at another wavelength, shockingly, they will be brighter at that other wavelength as well. So many people do correlations on a log-log plot and shockingly find a correlation because brighter things are brighter. And so this means you have to be very, very careful with AGN, which are systematically found in the brightest systems, that you're doing sort of a nice matched sample of the same galaxies with AGN or without an AGN. And so it makes for very complicated survey design where you have to have large numbers of galaxies that you are observing. And so that's something we're working on. Me and a few collaborators actually put in a large program proposal for ALMA in the last deadline to try and do a more systematic large-scale survey where we're actually observing hundreds of galaxies. The proposal unfortunately got rejected, but we got good feedback. So hopefully next time we'll be able to do this a little bit more systematically, but we haven't been able to do that until very, very recently. Another thing you might expect in terms of observing just a single line is looking for basically large line widths that correspond to these outflows, because you need to get this molecular gas to reach escape velocity essentially for these galaxies. And so we do see that actually in local active galactic nuclei. So this is an example of a local system, Markarian 231, I think it is, for anyone who cares about astronomical objects. And so this central peak here, that's just the molecular gas that's in the galaxy. And you can see this very broad wings down here, and that's the molecular gas that's escaping that galaxy. The problem with this is that it requires a significant amount of telescope time, right? This is the nearest, brightest AGN that we know, and it took a few tens of hours on the telescope to get this observation. You put this object at 10 billion light years away, and suddenly you need hundreds of hours just to make an observation of a single object. So that's pretty much a non-starter in terms of making an observation. So we can't really do this for galaxies in the early universe. You can do some absorption features for really rare molecules so that are trapped in these winds, but we don't have those as well calibrated in terms of gas masses as we do carbon monoxide. So some people have started doing that because the sensitivity of ALMA finally lets you get some of these ultra rare strange molecules like CH plus and things like that. But it's not entirely common yet. The other thing you could potentially do is do CO line ratios. And the great thing about that is that it kind of can avoid these mass biases, because when you're doing a ratio of one carbon monoxide line to another carbon monoxide line, you're scaling out the brighter things are brighter factor. And so ideally, what you're doing is you're mapping a full CO spectral line energy distribution, so a CO sled. This is what's shown in the bottom right here, where you're basically mapping the intensity of the line as a function of the rotational quantum number for that line. And then you fit it to one of these radiative transfer models. Ignore the fact that the lines are connected here. That's just for easier visualization. It's quantized, so obviously there's no data in between these 2 points. But you can fit one of these models and you can see multiple components potentially to the shape of the CO sled, where the primary component that's exciting the lower J CO lines is the heating for star formation, and these higher J components require some additional heating mechanism potentially related to the AGN. Again, this is something that we've seen for maybe a couple of local galaxies, but we haven't really necessarily had the chance to do at high redshift just yet. And if you're observing all of these CO lines, that again requires a significant amount of telescope time, so it's hard to do. You can also try and do it cheaply, which is instead of observing all of the CO lines, just try and find the right pair, and maybe that ratio will give you a measurement of how the AGN is potentially affecting the molecular gas. Again, this is hard because we need to disentangle these effects of the starburst and the AGN on some of these lower J lines, where just heating from star formation is sufficient to excite them. And then if you're in these higher J lines, that may not necessarily represent the bulk of the gas in these systems, because you need temperatures of a few hundreds of Kelvin versus most molecular clouds, which are like 20 or 30 or 50 Kelvin. So there are some challenges in here, but these ones that are using line ratios seem to be easier at high redshift than these individual line detections. So in terms of well-chosen line ratios, so once the sort of in the early 2010s, when we finally got access to CO1 to 0 at high redshift, some of the early work that I was involved in noted that the 3:2 to 1:0 line ratio suggested very different gas condition in these AGN versus starbursts. However, these initial observations were really based on a very, very small number of detections. So this is the cumulative fraction from these original works in 2010 and 2011. And you can see that there's something like 5 AGN and a whole 8 starbursts in this sample, not what one would call statistically significant. So during one of my postdocs, basically what I went and did was found for everything that in the literature so far that already had a CO3:2 detection, I went to the VLA and measured the CO1 to 0 line. So that way we could build up a more valid sample in terms of the number of galaxies involved. And unfortunately, the significance of this sort of separation between these two distributions disappeared when we got a larger sample. There's still some slight offset between them, but it's actually, if you do a KS test, it's not statistically significant at all. And so part of the thing that we think is going on here is that this classification of AGN versus a starburst is sort of an oversimplification, because AGN can differ in terms of their brightness. How strong of a starburst is it really? And so we really need some more quantitative handle for distinguishing between an AGN and a starburst, than rather this binary classification that is simply based on historical literature coincidence on basically whether or not somebody observed it in the X-ray first and identified it as an AGN, versus something that's really, really dust obscured, and so it's basically so optically thick at that point you can't even see the AGN in the middle, but maybe it does secretly have this buried AGN in it. And so we really need a better quantitative handle on this starburst versus AGN classification. So we think that we can do this with polycyclic aromatic hydrocarbons, so PAHs. So these large carbon rings are some of the bigger molecules we can find out in the interstellar medium of galaxies, and they emit quite strongly in the mid-infrared due to some vibration and bending and flexing modes in these large molecules, and they create these very broad features that you can see. However, under the harsher radiation field produced by the secretion disk of an AGN, these pH features actually get, pH molecules get destroyed by these sufficiently high energy ultraviolet photons. And so that means what you can do is use sort of the ratio of these lines to the underlying continuum strength as a probe of how much AGN heating of the dust is occurring in these galaxies. And a friend of mine, Alison Kirkpatrick, in 2015 showed actually that there is a significant amount of AGN heating of this dust, sort of beyond the immediate torus that's just down in the very central region of these galaxies. Once you reach sort of a critical fraction of sort of 50% of AGN heating in the of AGN strength as measured by these pH lines. And since the dust and gas are commingled, that means that these pH diagnostics kind of give us a handle on the total AGN strength in this system. So that means, so Allison and I went and basically did some archival research because it turns out the thing that you use for finding these pH spectra is the Spitzer Space Telescope, and it's out of cryogens, and it's past the end of its lifetime basically, and so you can no longer get spectra of these pH features at all anymore. So we went and found basically every source that had a pH feature and had an existing CO line somewhere in the literature, and tried to see what are the average properties of the CO spectral line energy distributions for things sort of above and below this 50% threshold. We of course have to do some complicated averaging to get rid of the whole brighter things are brighter effect, so that way when we're taking a median value, we aren't being biased by a few outliers. But so in this plot on the left, which is a measure of one of these higher J rotational lines in ratio to the 1 to 0 lines, it's all normalized to 1 here. Each dot is a galaxy with an individual CO line detection, and each line is sort of connecting, each of these thinner, fainter lines is connecting the CO sled for an individual galaxy. And we average them together, and we kind of see this suggestion of a systematically higher excitation for all CO lines for the AGN dominated ones versus the star-based dominated ones. But we have such poor statistics in terms of the number of galaxies that are in this sample, even still, that it's really not statistically significant at this point. And the plot on the right is basically the same thing, plus a few very well-known galaxies to astronomers, but they don't have these mid-infrared spectra, so they were not involved in the classification scheme over on the left. So it's, again, tantalizing suggestions that this is going on, but not quite there yet. So the next step is basically just expand the sample. Everything that has this IRS spectra, go and get new CO lines for the ones that don't have those CO lines already, or fill in the gaps in the CO lines for these systems. So this is something I've started doing. So I've gotten CO 1 to 0 for an additional 16 galaxies to hopefully expand the sample. And I'm working on writing that up. And we got a preliminary subsample for some of these higher J lines at the telescope NOEMA, the Northern Extended Millimeter Array, which is in the French Alps, to prove that these objects are what we say they are, and hopefully in the future we'll be able to get some more time to finish filling out these upper J transitions. But this is a work in progress, so we don't have the answer yet, but that's sort of the next step there. Briefly, the other thing we can do is, again, look at these extremely high JCO lines that might be tracing these additional heating mechanisms like X-ray heating or cosmic ray heating or just mechanical heating from turbulence in the centers of these galaxies. And luckily we have this nice reference sample for local systems where these CO sleds were found to follow some very, depending on, you could classify them into some typical shapes based on the ratios of the line luminosities. And some of these systems are clearly starburst dominated and have the right ratio such that they're in this alpha less than 0.3 class. But these ones that have this other combination of line ratios, these things absolutely 100% require some additional heating mechanism beyond just heating from the photons from hot young stars and star forming regions. They need some additional heating from presumably the AGN. And many of these systems like Markarian 231 are well-known AGN. But this is for the local universe. It's can we do this in the high redshift universe? So let's see, a year or two ago, I got new observations with ALMA. So this is building off of another collaborator's work, Axel Weiss, in sort of the initial cycle of ALMA, got a few of these very high J lines. And so then I got the next sort of 1 to 2 higher JCO lines that were in standard ALMA bands while they were still commissioning ALMA. Not all of the bands were supported and it was a little bit harder to get time on non-standard bands. Anyway, so we observed another 6 sources and got, J upper rotational lines of 10 to 9 transition all the way up to the 16 to 15 transition, depending on the precise redshift of the object. And so some of these are interesting objects, like this is an AGN and starburst pair with another little galaxy. Some of these things are gravitationally lensed, actually. So there's the multiple images of the same galaxy, but at the angular resolution of the telescope, we can't necessarily get a very pretty image. Since we were just trying to do a detection experiment, we were not trying to spatially resolve or map these galaxies to make pretty astronomy images. Sometimes we get accused of being blobologists as high redshift astronomers. And so this is some of the work that Rennie and Cabran were working on. So they made all of these maps and extracted all the spectra. And so these colored curves are the CO spectral line energy distributions for these galaxies. And we see a number of sort of interesting things here. Many of these systems show higher excitation than any of the 3 classes of lower redshift galaxies. So these shaded curves are where all the CO spectral line energy distributions work for local nearby galaxies. And some of these high redshift lines show way higher excitation than any of those. Many of these that have these very high excitation are things that are known to have an AGN in them, like the cloverleaf, like BR1202 South, but not all of them. BR1202 North is, again, one of these things that people think of as just being a pure starburst, but it's the most highest excitation of them all. So maybe there is an AGN and it's just buried. We don't have IRS spectroscopy, so we can't say. It's very frustrating. Of all of these systems, only PSS 2322 is the one that actually requires these additional heating mechanisms. So if you do one of these radiative transfer models, all of these are well fit by a single temperature and a single density. PSS 2322 is the only one that requires multiple temperatures and multiple densities to reproduce these line ratios. Another sort of interesting thing is that if you look at the width of these spectral lines as a function of the upper level of the rotational transition, some of these systems actually show really dramatic differences in line width as a function of J. So these very high JCO lines for BR1202 North are like almost twice as wide as some of the lower J lines. Now, not all of these spectra are good enough that you can actually measure the line width. And the line width has, again, to do largely for dynamic effects at this sort of scale. So it's probing the velocity and outflows of the gas in these systems. Also for this other thing that's known to have an AGN, also shows much higher line widths at higher J than at these lower J transitions. So that complicates things a bit because that means that these lines, if they have different velocities, are probably coming from physically distinct regions within the galaxy compared to these other lines. So you cannot actually you cannot model the CO spectral line energy distribution with a single component model, because there isn't a single component. So that's also something we need to look out for. So hopefully we'll be able to sort of expand the sample to look at higher J lines for more systems, now that we kind of see these weird effects in just the handful of things that we have observations for so far. But again, these observations are hard. Each of these detections, so this is a preliminary sample, and so because it's a preliminary sample, that basically means I went after the brightest and easiest things. So that's like an hour or two per line. You know, anything that's dimmer, you know, basically it goes as the square root as the integration time to get the same brightness sensitivity level. So for something that's, you know, twice as dim, you need to integrate 4 times as long. So that means it can be hard to get enough telescope time for everything us astronomers want to do, which is a lot. So basically, just to summarize, you know, evidence for AGN feedback affecting galaxies, star-forming molecular gas is hard to find and really pinpoint in the early universe. These higher excitation CO lines in AGN are not surprising. We've known about it in local galaxies for a while, but identifying sort of a systematic correlation with AGN strength or evolutionary state is still a challenge. We just don't have necessarily the angular resolution on the sky or these PAH features for every single object, because again, Spitzer is dead, so we can't get that new data. The very high JCO lines may require some additional heating mechanisms, but only some full width half maxes show that there is this distinct separate region, and we really need larger sample sizes for more quantitative AGN diagnostics. But ultimately, the goal is something like this that I've been working for a long time, where we have some CO line ratio versus some AGN versus star formation diagnostic, and we want to identify the starbursts, which would generally speaking have high line ratio, excitation line ratios, and the AGN quenching candidates, and then we can start working on the physics that's connecting from here to here, once we can actually clearly identify our molecular gases in a starburst and a molecular gas in an AGN quenching candidate. So with that, I'll leave it and I'll take any questions. Thank you.
Great. So thanks very much for this very exciting, very interesting talk. You know, it's like it's I think a long time since we've heard an astronomy talk. I think the last time we had an astronomy talk was last year. Mm-hmm. So yes, please have just any questions, especially undergrads. So let me start with maybe a simple question, a very naive question. So you're a radio astronomer, so you're looking at these spectra that come out from these molecular spectra that are in these galaxies, but they're really far away. Mm-hmm. So we would typically imagine that, you know, if it's dipole radiation, we would expect that, you know, it would come out as, you know, would decay as 1/4 pi r squared. Mm-hmm. How do you even get anything on Earth? How do you even measure any spectra on Earth?
Well, first of all, since the dynamics of the, you know, we're talking huge molecular clouds here, right? So these molecular clouds have masses of, you know, hundreds of thousands to millions of times the mass of the sun. So it's not going to be a nice coherent radiation source, since all of the molecules are pointed every which direction. And, you know, when you're talking about just that much material, you are definitely going to, you know, get some photons out of it eventually. And it's just, there's so much there that it's sufficiently bright. So if you're talking over the entire galaxy, one of these galaxies will often be just in the luminosity from this line, it will be 10 to the 10 times the luminosity of the sun in just a single line. These clouds are also, they have some structure to them. When we model them, obviously we're doing the simple naive, monodensity spherical cow sort of thing, but there is some density structure. And so oftentimes these clouds are known as being optically thick. So that means that any photon being produced by a molecule will immediately collide with another molecule and be absorbed by it. And so there is a certain amount of, absorption and emission that's going on to keep these clouds. And oftentimes you're only actually seeing the optically thin sort of outer layer of these clouds that's producing a lot of the emission. But yeah, there's just a lot. There's a lot of molecules there, and that's why we see them.
Okay, sure. More questions. I think I saw some raised hands initially, but maybe they've left already.
Yeah. Hi, I have a simple question. So actually, I would just like to ask, so in the starting, you mentioned about microwave background maps. So I would just like to know, what are these maps and how do you interpret things out of them?
Let me see if I can switch that slide. So the cosmic microwave background, again, it's microwave wavelengths. This is a particular example. Is this the Planck one or is this the WMAP one? I think this is the WMAP one. Anyway, it's a space telescope. One of these missions, they just basically mapped the sky using, I guess microwave. So I guess you need something kind of like a radio dish, and just count photons from every position in the sky over the entire 4 pi steradians or whatever. And if you measure at multiple different frequencies, you get sort of a more or less a perfect black body of emission. And then when you subtract off this sort of single temperature black body emission, plus sort of the velocity components for the satellite's motion, you can get some 1 part in 10 to the 4 fluctuations in terms of the temperature of the sky as a function of position. And so this microwave background, we also refer to this as often as the surface of last scattering. So that basically means as the universe expanded and cooled early on, again, it was optically thick emission. So basically it was dense enough that every single photon produced would then immediately get absorbed by another hydrogen atom. But when things cooled enough, well, okay, not a hydrogen atom, but anyway, the photons could then free stream towards us. And so the cosmic microwave background at redshift 1100 or so basically is this surface at which we can, the universe becomes transparent. And before that, the universe is opaque and you cannot see really necessarily anything. And so these photons from the temperature of the universe back then, as the universe expanded, they stretched in wavelength. And so now it all corresponds to microwave wavelengths when we observe them today. So this afterglow of the Big Bang is the hot glow of the soup that was the universe until it finally got low enough density that the photons could come towards us.
Nice. Thank you.
More questions? I've got one question. So again, you're an observational astronomer. You're trying to identify these AGN quenching candidates, and it's through you had these names BB2253 something something.
Mm-hmm.
You say you weren't really sure if it really was an AGN or not. Perhaps it was kind of hidden there or not hidden there.
Mm-hmm.
So in the grand scheme of things, when you kind of identify such candidates or no candidates or your suspicions of what these things are, how does that fit into this kind of timeline picture, which you said it started with the starburst, it did this, it did that, and you were hoping that at some point it might become elliptical galaxies, right? So you make some observations, you have some candidates. These are just maybe 2, 3, 4 galaxies, maybe?
I mean, for the ones that we have molecular gas detections of, yes. But
and then after that, how do you make that kind of extrapolation to understand the life cycle of these galaxies?
So okay, there's a lot of things going on in the simulation work here. So one of the things you can do is again, detecting these galaxies in the early universe is hard. So you start by studying the nearby systems, right? Because they're just intrinsically brighter because, you know, great 1/r² laws. So you also can detect the systems that are intrinsically lower mass, so you have larger sample sizes. And what you can do is basically look at the number of systems that have any sort of AGN signature at all in them as a function of galaxy mass locally in the present day. And you can kind of roughly, using this idea that you can kind of paint on a galaxy of a specific mass to a specific dark matter halo to earlier periods of cosmic time, because you know that these dark matter halos just have to accrete material as they go. So you know that a certain mass system today probably had a certain mass progenitor earlier in cosmic time. And then you can then make a few observations, the few that you can make, of these mass systems and earlier in cosmic time, and just kind of see if they correlate. So you can't actually, unfortunately, follow a single galaxy to the present day because we only get specific snapshots the further and further away we're looking. But we kind of can, you know, look at different slices of cosmic history and see if the numbers sort of make sense.
It's like a polling.
Yeah. It's so it's tricky, and like this picture of these mergers and these dusty starbursts. You know, this is the kind of rough qualitative picture. It's almost like the theory of evolution, that stuff just kind of makes sense and systematically supports each other, but like, you know, there's no single smoking gun necessarily that says this is definitely happening. There are people who do like more complicated hydrodynamical simulations, where they not only do the dark matter, but they actually include all the baryonic physics and the gas and the star formation and all of those processes as well. And they're making a lot of progress in doing this, but there's just a lot of knobs to twiddle in these simulations. And one gets concerned that in tuning everything to reproduce the present day, they're not necessarily probing the underlying physics as well as we would like. So, you know, there is work on the simulation side of things too that kind of supports this picture, but again, there's a lot of uncertainty on the knobs, and a lot of these knobs do not correlate to an observable necessarily, so we can actually test if that's what's really going on.
Great. So I think it's very important that we get to the students.
Okay.
So I think Danchi has a question, and then we can go to that chat message question from Trialin. So we can go first to Wang Danchi.
I can't actually see the chat message.
Yeah, I'll read that out afterwards.
Okay. Hi, Professor. Thank you for giving us this informative talk. I'm actually did a project on cosmology, and I realized that all modern cosmology, at least accepted ones, are based on lambda CDM, which is assuming the universe is homogeneous and isotropic, spatially isotropic. But yeah, maybe I'm looking more at the composition slide, yes. But then I just saw a video by some physicists that she said that when we look at things like we drop this isotropic, spatially homogeneous requirement universe, that the composition of our universe will be different. So I would like to know, what's your view on that? Thank you. Yeah.
Sorry, the what of our universe would be different? I missed that.
The content, the composition, yeah. Like how our universe is made up, like dark matter, dark energy, yeah.
Oh, I mean, so the relative energy density of these various components does change as a function of cosmic time. So, you know, this dark energy is proportional to the amount of empty space that exists. So that means the further back in cosmic time you go, there would be a relatively lower dark energy fraction in terms of the total energy density. So there were periods of cosmic history that were matter dominated. There were periods of cosmic history that were radiation dominated as time went on. And so we just happen to be in this dark energy dominated phase of the universe as it is expanding. I hope that addresses your question.
Yeah, thank you so much.
Okay, so the chat message question is a direct question about your blob science. So naive question here says, GLM, to my understanding, redshifting is frequently considered in measurements, but is there any other factor that can tamper with the redshifting process other than distance alone?
Yes, so you can have, we often refer to these as peculiar velocities. So if you have like one of these,
great name. Great
yeah,
name.
we're very descriptive with our names in ways that is not very creative, but descriptive. And so if you look at sort of this picture of the distribution of galaxies as a, you know, a function of distance away from us, essentially, right? So we can, these galaxies are falling along these cosmic filaments to a node. And since they're falling, there is just a basic Doppler shift associated with their motion, in addition to the redshift associated with cosmological expansion. And so you have to correct for this peculiar motion that's just due to the dynamics of what's going on with that galaxy as well. And so the other funnily named feature when you look at one of these observations of the distribution of galaxies, if you don't correct for these peculiar velocities, you end up with, again, since you can only get the component of the velocity along our line of sight, that means that galaxies tend to be smeared out, their velocities smeared out relative to us when you try and use it to directly infer their distance. So you get, instead of just like these nice little nodes, you get kind of elongated elliptical features that all point towards us. And we refer to those as fingers of God, because they all look like they're pointing back to us. You know, once we correct for those, this all sort of go away. But those are this peculiar velocities associated with the motions of these galaxies as they're falling along the filaments to a new center of mass.
Right, more questions.
Hi, can you hear me?
Yes.
Yes.
Yes. Okay, so I'm Zia, the one who asked the question before. Actually, I was thinking about more along the lines of like, because we learned about like maybe Compton scattering like last semester, like when photons hit into like other particles, it refracts with a different wavelength because it kind of loses energy. So actually, for the previous question, I was thinking more along the lines of whether the light would run into like, maybe it runs to an area densely packed with matter, and then it gets reflected off, and then it loses energy, and then when it arrives on Earth, it has a different wavelength from what we would expect from the original distance. So yeah, that's what I was. Yeah, thank you for the information. Yeah,
I mean, like, you do have to be worried about absorption and scattering effects as well, and so that tends to really mostly affect the shortest wavelengths of light. So optical and ultraviolet is where we really have to be concerned about a lot of this scattering. So this is why, for example, in this image of this galaxy here, you see all of this dark material. So this is all of the dust in this galaxy that's absorbing the optical wavelength photons being produced by the stars in this galaxy. So there's plenty of stars in this disk, and it just looks dark because of these lanes of dust and gas that are absorbing those photons. And so that happens, you know, obviously more strongly where there's the most dust and gas, which is inside of a galaxy. But, you know, there is, you know, some of this material is in these cosmic filaments. And so you do get sort of larger, long wavelength. So you do get additional absorption potentially from the ionized material in the intergalactic medium that can cause, absorb photons even potentially from the CMB, or scatter them more often. You can up or down scatter them to slightly different wavelengths. This is called the Sunyaev-Zeldovich effect for clusters of galaxies. The hot X-ray gas in these clusters of galaxies, the photons coming from the cosmic microwave background will get, it's been a long time since I've thought about Sunyaev-Zeldovich effect. It's, is it Compton scattering? Is it some one of these scattering mechanisms I'm forgetting the name of right at the moment. And so all of the photons of certain wavelengths produced by the CMB get scattered up to a slightly different wavelength. And so if you were to do like a 3-color image at different wavelengths of the CMB where a cluster of galaxy is, it will be a hole in the CMB at one wavelength and a particularly bright spot in the CMB at another wavelength. So
sounds like Compton.
Yeah. So you can see these effects as well in the CMB, and so this is one of these things where one man's trash is another man's treasure, and so there are people who study galaxy clusters. So the people who study the cosmic microwave background are like, oh God, get rid of these galaxy clusters. We don't want this as obscuring all of our beautiful cosmology work. But the people who study galaxy clusters are like, hey, observational signatures. What science can I do with that? That is something that people have to correct for.
Very good. That was an
you,
excellent question. Yeah, very good. More questions. Let me ask one question, and perhaps it's kind of like a kind of more basic foundational question. Why do we expect a supermassive black hole in the heart of most galaxies? So you made that statement quite early on, and this kind of connects with this Nobel Prize. So why is this so common, and why do you expect it in most galaxies? Is it just a fact of life? Will you always have some agglomeration, and that always happens? You also made one other statement, which was you have this dark matter and you have other matter that tends to get attracted to this, and that forms your galaxy. Is this somehow connected?
Yeah. So the fact that most galaxies have a supermassive black hole in their center, this is an empirical statement. This was not necessarily expected. This is not a prediction. This was just something that people found.
Sure, but is there a physical reason why? As in, like, is there any kind of rhyme or reason why this happens, or is it just law down from Sinai?
We don't really know how, honestly, how supermassive black holes form is a very open research question. We don't know. Given the accretion rate we can infer for supermassive black holes based on how much material they're sucking in their accretion disk, the accretion rate is actually not high enough such that we should have black holes of the masses that we see today. They're too massive just based on these accretion rates. So that tends to make people think there must have been some sort of seed black holes earlier in cosmic time. We aren't certain where those seed black holes came from. Now, some of them, as you know, with like LIGO, is detecting more and more massive black holes that are on the order of 50 to 100 solar masses. And these are black holes that are colliding with one another to form even larger black holes. So we know that some black hole growth can occur just by black holes smashing into one another. We also know that the first generations of stars were even more massive than today's stars because they didn't have, there were no metals around in the early universe. So the gas couldn't cool to fragment into smaller clouds, which meant that all of the stars that formed were extremely massive. And then they died really fast and presumably left behind quite massive black holes. But again, those shouldn't be much more than hundreds of solar masses, we think. It's a far cry from the billions of solar masses today. There are also people who do these basically cosmological simulations where they're tracking how the baryonic material cools from the early universe to today. And there's some suggestion that in some cases, the overdensities of baryonic material are actually, instead of collapsing to form a star within a galaxy, might directly collapse into a black hole. In the early universe, there's been some simulation work that suggests that. We don't have really any observational evidence that we can confirm that with, though. So we really don't know where these supermassive black holes come from. It's kind of a mystery, but they're working on it.
Okay, I think there's one final question, that's in the chat. So Sunny Comprado asks, are there any observable structure of the black hole other than the accretion disk where research can be of interest?
Yeah, I mean, so there are different structures you can measure around black holes. Besides the accretion disk, there's also the dusty torus. There are also these jets that come out of some of them. When you have, black holes are fundamentally very high curvature regions of space-time, and so that means you have gravitational lensing as well. And so that means you can look at the distortions of background images relative around these black holes and say something about the mass structure of the black hole potentially. And so you can use gravitational lensings effects to potentially characterize your black holes. You can do potential, usually this isn't done for no, actually, maybe you do this a little bit for black holes. You can do timing delays, right? The photons that are near one side of the black hole will take a different light travel, take a different amount of time to reach you than maybe some photon being produced on the other side of the black hole relative to you. So you can look for time fluctuations of variable features in the accretion disk around the black hole and potentially use that to say something about the system. Those are sort of the main observables that I can think of, at least when it comes to supermassive black holes. You can also, for stellar mass black holes, you can also do interesting things. Nearly half of all stars are in binaries. And if one of those binaries went supernova and left behind a black hole, you'll find a star orbiting another black hole. And you could potentially do some science with that because you can detect the photons produced by the star in the binary. Yeah.
Excellent. Thanks very much. I think we've asked you lots of questions already. Thank you for the very interesting talk. And I'm sure the interested students, if you have more questions, please approach Chelsea by email or something. And so she's right here in Singapore, and so it's same time zone, so you can kind of talk to her. So with that, we want to thank you for this very, very interesting talk. And thanks very much. So I think that's the end. Thanks.
Okay, great. Thank you so much all. And yeah, feel free to shoot me an email. It's chelsea.sharon@UYale-NUS.edu.sg. So just Google me, you can find me.
Great. So David, we stop the recording now?
Yes, I think it's okay. Thank you very much for the nice talk. So let me remind you that the talk has been recorded. And so if you want to see it again, you can come to our website. It will be posted very soon. Thank you very much, Chelsea. Right. Take care and goodbye, everybody.
All right. Bye. Thanks, everyone.
Bye.
Bye.